12 C waves. 12.8. Defining waves. The sound waves of cheers throb in your ears at a baseball game. Water waves wash gently ashore or cause great devastation as tsunamis. The ground shakes as waves from earthquakes pass through it. Waves surround us, moving energy from here to there. We hear because of sound waves and see because of light waves. Waves are periodic changes that transmit energy from one place to another. Waves in matter, mechanical waves, periodically displace particles around a relatively stationary position. Though the individual particles periodically oscillate as the wave passes, there is little or no overall motion of matter. Electromagnetic waves, see Chapter 14, transmit energy without matter. 12.9 Describing waves. Waveform. Figure 12 to 20 shows a cross-section of a typical waveform. The highest points of a wave are crests, and the lowest points are troughs. Midway between these 2 points is the wave's rest position. The distance of a crest or trough from the rest position is the amplitude of the wave, similar to the amplitude of any other form of periodic motion. One cycle of a wave consists of one complete crest and trough. The length of a wave cycle, or its wavelength, is the distance between corresponding parts of 2 sequential waveforms, such as from one crest to the next, or from one trough to the next. Wavelength is represented by the Greek letter lambda. Wave frequency. The frequency of a wave is the number of wave cycles that pass a given point in 1 second. Similar to other periodic motion, wave frequency is measured in hertz. Multiples of hertz using SI prefixes are commonly used for waves with high frequencies. 1 kilohertz equals 1,000 cycles per second. 1 megahertz equals 1 million cycles per second. And 1 gigahertz equals 1 billion cycles per second. All mechanical waves require a medium, the matter through which waves travel from place to place. However, the particles of the medium do not move very far from a given spot compared to the motion of the wave. How can this be? Figure 12-21 illustrates one form of particle movement found in water waves. As the wave surface oscillates up and down, the particles within the wave move in a circular path. As the wave passes, they return to their near starting point. Their nearly circular motion clearly demonstrates the cyclic nature of this periodic motion. This idea is easier to visualize on a vibrating string. When you pluck a long string, the vibrations clearly travel down the string, but the string particles, the medium, travel with the wave. No, they only move up and down or side to side. Other than the up and down motion of the wave, the particles of the string remain in place. The path of the wave is different from the motion of the individual particles that are disturbed. The wave carries energy by transferring oscillations to adjacent particles, not by carrying the particles along with the wave. Wave speed. How fast do waves travel? Wave speed depends on the wave type and its medium. For example, sound waves travel at about 300 meters per second in air, 1,533 meters per second in seawater, and 5,130 meters per second in iron. The speed of sound is also subject to factors such as temperature, relative humidity, air pressure, and density, depending on the medium. Surface waves in water occur where air and water meet. They are different from sound waves in the way the water particles move as the wave passes through. The speed of surface waves depends mainly on the depth of the water compared to their wavelength. Waves in deep water can move faster than waves in shallow water. Typical wind-driven waves have speeds of a few meters per second. Earthquake-generated tsunamis can travel at over 200 meters per second, more than 700 kilometers per hour. The fastest waves in the universe are electromagnetic waves. These waves zip through space at an incredible 300 million meters per second, fast enough to get from the Earth to the Moon in 1.3 seconds. Electromagnetic waves slow down when they pass through matter. The speed of a wave is mathematically related to wavelength and frequency. The following equation expresses this relationship for most waves, when all other properties in the medium are constant. V equals lambda times F, where V is the wave speed in meters per second, F lambda is the wavelength in meters, and F is the wave frequency, in cycles per second, hertz. A single wave cycle, or a very short burst of waves, is called a pulse. If you stretch a rope out and then pluck it once, you can see the pulse move rapidly down the rope. Sound wave pulses occur when animals produce clicks or chirps. Sharp volcanic explosions are pulses of sound and seismic energy. Humans use pulsed sounds for alerting others, a whistle or a yell, for instance, or in sonar to track fish or submarines. Similarly, radar pulses are used to determine the range and direction of moving objects in the air and on the ground. Wave energy. Mechanical waves exist because they transfer energy through matter. So, how much energy does a mechanical wave contain? This question is not easily answered, just as we could not state how much thermal energy an object contains. However, the rate at which a wave transfers energy, or its power, is proportional to its amplitude squared, assuming that the wave's period is constant. Thus, if the amplitude doubles, the power quadruples. This exponential relationship is one reason why large ocean waves can damage beaches much more quickly than small lapping waves. The energy in electromagnetic waves can be measured because this kind of non-mechanical wave comes in separate packets of energy. The energy of each packet is directly proportional to the wave's frequency. So, as electromagnetic frequency increases, its energy increases. See Chapter 14 for more information on the energy in electromagnetic waves. 12.1 Classifying waves. Waves are classified according to the direction the particles in the medium move as the wave energy passes through the medium. If the vibration is at right angles to the direction of travel, the wave is a transverse wave. The vibrations of a string are an example of a transverse wave. Note in Figure 12-25 how the points marked on the string do not move along the string, just perpendicular to it. The wave crest is formed as particles spread out in one direction perpendicular to wave direction. The trough is formed as particles spread out in the other direction. Light and other forms of electromagnetic energy are transverse waves, although these waves don't involve particles of matter. The electric and magnetic fields change in a periodic way that appears like a transverse wave pattern. If the vibration of a wave is parallel to the direction of wave movement, it is a longitudinal wave. Sound waves are the best examples of longitudinal waves. These waves form as particles are shoved together in compressions or spread apart in rarefactions. The compressions correspond to wave crests, and the rarefactions are like wave troughs. If you graph the density of the particles in the longitudinal wave's medium with time, you can observe the familiar wave-like shape of the graph. See Figure 12-26. Water waves and certain kinds of earthquake waves are not simple transverse or longitudinal waves. These waves occur at the boundary between two different media, for example, between air and water. The individual particles in these waves move in circles or ellipses and have both transverse and longitudinal motion. 12th wave phenomena. Nearly all waves have similar behaviors. Let's consider the ways that waves interact with matter and with each other. Reflection. If you stretch a rope taut and then pluck it once, you can see a pulse move rapidly down the rope. If the far end of the rope is fixed, the pulse will bounce back. The wave is reflected along the string in the opposite direction. Reflection occurs when a wave bounces off a surface that doesn't completely absorb its energy. The reflected wave may change depending on how it reflects. If it reflects off a hard surface, the outgoing wave is flipped, though its amplitude is unchanged. If the reflecting surface absorbs some of the wave's energy, then it is flipped and its amplitude is smaller. In every case, energy is conserved. Reflection is used in many ways. Light waves generated by a flashlight bulb reflect from the concave mirror behind the bulb to produce a beam of light. The dish-shaped antennas used for radar and television waves, the concave mirrors of large optical telescopes, and the acoustic shells placed behind orchestras all concentrate waves in a more useful direction. When a wave moves from one medium to another, its speed changes. This phenomenon is called refraction. Under most circumstances, a wave bends from its original path when it enters the new medium. For example, Light waves bend as they pass from air into glass or from glass into air. Bending does not occur if a wave enters the new medium, perpendicular to the boundary between the media. Waves with shorter wavelengths are refracted more than waves with longer wavelengths. For example, when visible light passes from air into a glass prism, it is refracted. The different wavelengths of light are refracted at slightly different angles. Blue light has a shorter wavelength than red light, and it is refracted at a greater angle. This is why prisms disperse light. Sound waves are also refracted. It's far from quiet beneath the ocean's surface. Besides the biological noises of shrimp snapping, fish grunting, and whales singing, man-made noises from ships and other marine activities can be heard. Water temperature and pressure differences alter the acoustic medium, and these differences affect the way sound waves spread out through the ocean basin. Thus, sound waves bend down and up in deep water, sometimes repeatedly, and can travel hundreds of kilometers. Sound refraction in the ocean is especially important to submarines and to those who hunt them. When the speeds of a wave in two media are greatly different, some of the wave's energy may be reflected as well as refracted at the boundary between them. This is especially true for shorter wavelengths, which are more easily refracted. It's also especially true as the wave's angle decreases as it approaches the boundary. For example, a swimmer at the bottom of a swimming pool can hear the voice of someone shouting directly above him at the surface much more clearly than someone shouting at the far end of the pool. This is because the sound waves from the person overhead are closer to perpendicular as they move from air into the water. Wavelength changes from one medium to another because wave speed changes. Recall that V equals lambda times F. See figures 12-28 and 12-29. The frequency of a wave is determined by its source, and it remains unchanged as long as the wave exists. However, denser media slow waves down, so the wavelengths must shorten in proportion to wave speed. Wave interference. Picture two boys holding a long, slack rope between them. At the same instant, each boy flicks his end of the rope upward, sending a pulse toward the other. What happens when the two pulses meet at the center? Since both pulses are upward displacements of the rope, they are added together for a brief instant as they pass through each other. At that moment, there's a single pulse, whose amplitude is the sum of the amplitudes of both pulses. They do not stop but travel on as before. The ability of two pulses to encounter each other, survive, and move on as before comes as a surprise to many people. This phenomenon, though, fits the predictions of the law of the conservation of energy. The boys repeat the experiment, but one of them flicks the rope downward as the other flicks it upward. When the two pulses meet, one has an upward displacement and the other a downward displacement. What do you think will happen this time? If the pulses are of equal amplitude, there will be a brief moment during which they cancel each other. The rope will appear to be approximately straight, though both the waves and their energy are still present because the rope is moving and not still. Then, the pulses will pass by each other and move on unchanged. Many waves can combine in this way. When waves from different sources cross paths, their interaction is called interference. When the crests align with crests and the troughs with troughs, the waves are in phase. Their wave heights are added together, producing high crests and deep troughs. This is called constructive interference. If the crests align with troughs and the troughs with crests, destructive interference occurs. The waves are out of phase, and their wave heights are subtracted from each other, producing smaller crests and troughs, or even briefly canceling the waves completely. When waves with different wavelengths and amplitudes interact, both kinds of interference occur at any given moment. Constructive interference can be dangerous to ships at sea. Ship captains have seen small waves come together in phase to form waves 15 to 30 meters high. Without warning, these waves can combine to capsize a small vessel. Destructive interference can also cause problems. Some auditoriums have dead spots, where it is difficult to hear even if the sound is amplified. Dead spots are caused by the destructive interference of the sound waves from two different loudspeakers. or from direct sound waves combining with waves reflecting off hard surfaces. What do you think happens when constructive interference occurs in an auditorium? When two traveling waves with exactly the same wavelength and frequency move through each other in opposite directions, a standing wave is formed. A standing wave appears to be stationary in the medium because the positions of the crests and troughs do not move. Instead, they rise and fall in place as the two sets of waves interfere with each other. Points in a standing wave that experience no vertical displacement are called nodes. The spacing of the nodes is half the wavelength of the waves. Beats. One form of wave interference is especially important to acoustics and structural engineering. When two or more continuous waves interfere, they are replaced by a set of waves with exceptionally large amplitudes. These waves have a lower frequency than the two sets of interfering waves and are called beats. Beats are especially noticeable when two audible tones interfere, sometimes producing an annoying, slowly pulsating sound. You may have heard such sounds during an airplane flight or boat cruise when the engine speed settings were not identical. The sound of the beat frequency can be very loud. Diffraction. Did you ever wonder why you can hear the voice of someone who is around a corner in a hallway? You might guess that the sound bends around the corner, and you would be correct. However, there is no change in the medium, so the sound waves don't bend because of refraction. What is happening? When a wave moves past a corner in its medium, it naturally folds or flows around the corner. This phenomenon is called diffraction, and every kind of wave experiences it. To understand diffraction, let's refer to a model of waves first proposed by Christian Huygens in 1690. His model is still useful today for explaining certain wave properties. Huygens recognized that waves are three-dimensional, and that most start at a source that can be modeled as a point. The waves spread out in a spherical pattern from the source. He suggested that every point on the spherical surface of a wave acts as a source of a new set of waves. Each of those new waves then spreads out in turn. When a wave surface moves past an edge of an opening or a corner, the spherical waves generated at the edge move outward, giving the appearance of the wave bending around the corner. See Figure 12-34. Since the diffraction directs more of the wave's energy straight ahead, less energy wraps around the edge, and thus a shadow zone forms behind the barrier. The effect of diffraction appears significant when the wavelength is large compared to the size of an obstacle or opening. For example, water waves that are several meters from crest to crest flow around a dock piling half a meter in diameter and merge back together. However, the same water waves will bend only partially around a small post with a diameter many hundreds of times larger than the wave's wavelengths. A shadow zone, an area lacking waves, will form behind the small. Sound waves are shorter than water waves, but they are still long around most average-sized objects, explaining why you can hear someone's sound around a corner. Light waves also experience diffraction, but because the wavelengths of visible light are exceedingly short compared to most obstacles, the effect is hardly noticeable. Light beams always form shadows when objects block them. Doppler effect. The frequency of a wave affects how we perceive it. For example, the frequency of a sound wave determines its pitch, how high or low the sound is. The higher the frequency, the higher the tone. Our eyes and brains interpret the different frequencies of visible light as color. Higher frequencies produce shades of green and blue, and lower frequencies produce oranges and reds. The source of a wave determines its frequency. However, an observer may sense a different frequency from that emitted by the source if he or the source is moving relative to the other. In general, as the source of waves or the observer move toward each other, the observer receives them at a higher rate than the source is emitting them, which means that the observed frequency is higher. Similarly, if the source or the observer is moving away from the other, the observer receives the waves at a lower rate, so the observed frequency is lower. This phenomenon was first predicted in 1842 by the Austrian mathematician Christian Doppler. His astronomical observations led him to predict that scientists would eventually be able to tell the speed of a star by its color change. If the star was moving toward the observer, the waves would appear to be closer together and thus bluer in color. If the star was moving away from the observer, the waves would appear to be farther apart and the star's color would be redder. This prediction was remarkable because no instrument existed then to measure the predicted color shifts. Doppler confirmed his theories with experiments using sound waves. He placed musicians on a train. They played single notes on their instruments as the car passed other highly trained musicians on the ground next to the track. These individuals wrote down the musical notes they heard as the train car passed. Doppler was able to demonstrate that relative motion between sound source and observer did indeed change the frequency perceived by observers. His findings were not immediately accepted by the scientific community, but eventually the Doppler effect was recognized as a property of all waves. You will learn more about the Doppler effect in later chapters. 12th, using waves to solve problems. Is there a way to use waves to accurately keep time? Can you think of the most accurate way to tell time? In 1955, Louis Essen developed the first atomic clock, which was more accurate than any pendulum or quartz clock had ever been. His clock produced an error of less than 1/300th of a second per year, or an error of only 1 second in 300 years. Many atomic clocks use a gaseous sample of the element cesium. When the gas absorbs radio waves at a particular frequency, all the cesium atoms vibrate together, emitting their own waves. The periodic signal, which is very steady, is used to drive the electronic circuits that indicate the time. The atomic clocks located at the U.S. Naval Observatory in Washington, D.C., are used to report standard time for the United States. Those clocks are so accurate that they will neither gain nor lose 1 second in more than 60 million years. The current definitions for the SI units of time, frequency, and length depend on the waves generated by the cesium atom.